Okay, I'm getting ready. Is it working? Okay. Is there a pointer? Nope. I have it, don't worry. Oh, yeah. I'm a prepared speaker. Okay. First of all, let me thank the organizers to putting together this wonderful workshop here in this wonderful environment and wonderful people, so everything's together. And thank you that I can talk about superconductivity with KKR. My name is Bálazs Újfalussy. I work at the Wigner Research Center for Physics in Budapest. And in the course of these results and theories, I work together with a bunch of people who are listed here. First of all, I want to mention Gábor Csire, who used to be my PhD student, and he did the bulk of the work. Bende Guznyári and András László, who work with me and László Szúnyog at the Technical University. I've got a collaboration with Kuyunga Park at Virginia Tech and James Annett, Martin Grethand in Bristol. It's a long tradition within KKR people. Stefan Schönecker in Stockholm, Hubert, and Jorge Quintanilla in the University of Kent. You have only 2 USB ports. That's, what? On the back side. Okay. Still no joy. So how can I?
Oh yeah, because it's now realizes the 2 screens.
Ah, okay. So little program. I'm going to talk about Bogolyubov-Deugen screen KKR formalism. As you heard in the first talk, generalizing screen KKR to Bogolyubov-Deugen or relativistic Bogolyubov-Deugen is a matter of triviality. So I don't know why I'm here. We'll talk about density functional theory, KKR, multiple scattering very little then, because it's a triviality. And then we try to interpret these results, because interpreting the Bogolyubov-Deugen is probably not what you have done every day. Look at quantum well states, proximity effects, spontaneous magnetizations, and surface states in topological insulators, and our quest for the Majorana fermion, starting with the Yushiba-Rusinov states in magnetic impurities, if I get there. So superconductivity is every textbook has it. It's been discovered by Kamerlingh Onnes, and the theoretical explanation came from Bardeen Cooper Schrieffer 40 years later. And this is what the textbook is going to teach you, that an attraction between electrons cause the formation of Cooper pairs, provided the screening effect strong enough to reduce the Coulomb repulsion. A Cooper pair has been thought of as a time inverse pair, an electron with a momentum k and the spin pointing up, pairs with an electron with minus k and the spin pointing down. and you can write the BCS wave function in this way. I don't want to go on to describe BCS theory. I rather point out that it was wonderful that it was able to show the mechanism of superconductivity, but it had problems. It's not very material specific. It only gives rough estimates. It's limited to V coupling, and it cannot be easily applied to inhomogeneous systems like multilayers. And the solution has been several ways. The Eliashberg equation was brought in to remedy that. That has a problem with the mu star. And the solution I'm going to go about is a Hartree-Fock generalized Cooper pairs with standard momentum operators, and it can naturally lead to a theory which can be applied to inhomogeneous systems. So Bogoliubov-de Gennes equations, we formulate it in terms of these field operators. I put this red circle there to point out that alpha stands for the spin quantum number there. They obey these anti-commutator rules. And we take this second quantized Hamiltonian, and then we assume that VR is a spin-independent potential. The electron-electron coupling is Pont-like and can be characterized by a single parameter coming from the BCS theory. Then we try to find an approximate solution of the many-body problem in terms of an effective one-electron Hamiltonian to minimize the free energy in a grand canonical ensemble. This idea was proposed by de Gennes. And this is this effective Hamiltonian. It's basically a Hartree-Fock Hamiltonian with some additional terms added to it. What I want to point out that it's called an effective one-electron Hamiltonian, but it is really about two electrons, and the up and down here doesn't mean an up and down component of a wave function, but it's the wave function on up and the down electron. So it's about two electrons. And this Hamiltonian then can be diagonalized with the Bogoliubov-Volatin transformation, written like this, with these gamma matrices are creation and annihilation operators for a Bogoliubov quasi-particle, often referred to as a Bogolon. And then you get this effective Hamiltonian after the Bogoliubov-Volatin transformation. And calculating these anti-commutators two different ways, one for the real Hamiltonian, then for the effective Hamiltonian, and then we arrive to the Bogoliubov-de Gennes equation, which tells what kind of conditions these U and V numbers have to satisfy in order to that effective Hamiltonian to be a solution. This U part is often referred to as an electron-like, and the V part is often referred to as a hole-like component of these equations. We'll come to that a little later. And if we require the free energy is minimized, then we get the condition for U and this delta, which is the coupling between the electron-like and the hole-like component. And these equations form a self-consistent equations. As you recognize, if somebody tells you U and V, you can calculate this U, the small u and small v, and from that you can recalculate U and delta, stick it in, and do it ad infinitum. The material-specific aspect comes by when we try to do the density functional theory for superconductors, put forward by Oliveira, Gross, and Kohn, 1988. I'd like to remind you the talk of Julie Staunton before, when she was calling attention to the density functional theory for magnetic system, where you have a charge in density functional, you have a charge density, and the energy is a functional of the charge density, and it reaches its minimum at the ground state density. In a magnetic system, this is replaced by the charge density and the order parameter, the magnetization density, and you minimize the energy functional in terms of the charge density and the magnetization density. Now this idea is applied here. We take the superconducting order parameter, and we take the energy as a functional of the charge density and the superconducting order parameter. And just go ahead with the machinery, write it down, try to calculate the minimum. You get these equations here, which gives conditions for both the effective potential and the effective pair interaction, which is now I'm using it in the correct way. The only problem is that we don't know this exchange correlation potential for superconductors. By the way, if you happen to know, don't hold back, because that's worth a Nobel Prize. Yeah, this is the equation we have to solve, and we have to say something about this exchange correlation potential. So this is the recipe. The Hamiltonian can be diagonalized by the Bogoliubov-Volatin transform. So you apply density functional theory, you get a Hamiltonian, a Kohn-Sham Hamiltonian, you apply the Bogoliubov-Volatin transform, and that diagonalizes the Hamiltonian, and the coefficients satisfy the Bogoliubov-Duhem equations right here. So this is now the agenda. You solve Bogoliubov-Duhem equation, you obtain V and U, stick it in the appropriate formulas to get rho and chi, and then you can calculate V effective and delta effective if you know the exchange correlation functional, and you go back and you can close the loop. It's easy to see now that we have a theory which is material specific, right? Because we talk about effective potentials and effective pair interactions, even if we don't know it. So there are various ways to go by this exchange correlation functional, and the way I was dealing with this goes back to Suhasini, Timmerman, and Jurfy. They proposed that you write it as a normal exchange correlation functional plus some integral kernel here. And then you try to analyze this integral kernel, and you assume that potentials are local. So that brings in a lot of delta functions here. But it doesn't get rid of the functional dependence of rho and chi. So as a good theorist, if I don't know the form of a function, I assume it's a constant. This is not from the devil, though, because in superconductivity there is a parameter called the electron phonon coupling parameter. So if you accept the approximation that you decouple phonons from electrons and you don't do the calculation dynamically, just calculate one phonon and one electron and somehow combine them together, this is actually a proposal which one can argue about. The good thing is that this parameter, which is the electron phonon coupling parameter, can be calculated within multiple scattering theory from the Gaspari-Jurfy formula, which I will do in a minute. There are much better theories about, however, Martin Lüders and I forgot his first name, Linschild, came out with a much more detailed and a dynamic theory where the phonon calculation is really embedded into the exchange correlation functional. But that's really complicated. So to learn the principles of Ubinitio theory, I went by the statue of Ubinitio and tried to become more clever. If you happen to be in Prague, don't miss this particular statue where you can see Ubinitio written on a stone statue. So the solution of the we still have to solve the Bogoliubov-Duhem equation. I just showed you a bunch of equations, but I didn't tell you how to solve it. And there are many ways to go by solving the Bogoliubov-Duhem equation. Here we are going to go by with a multiple scattering theory. There's already exists a solution. Gábor Csire made it within the Siesta code as well. So I recast the Bogoliubov-Duhem Hamiltonian in this way, where you have an H0. Consider this μ's here. That's the Fermi energy, and the potential term, which now has an off-diagonal component in electron and hole index, and those are the effective pair interactions. And of course, the solutions are normalized, and I can define the resolvent of this Hamiltonian is in the normal way. And because it's multiple scattering theory, I have to apply the muffin-tin approximation right here. And once I did that, I applied the same muffin-tin approximation to the effective pair interaction as well. Now, in principle, this effective pair interaction is a function of R within the muffin tin, and we calculated its R dependence and everything, but it turns out we lose very little if we replace it by a constant within each muffin tin. So this is how you make this theory work for a heterostructure. You can have different superconductor, non-superconductor materials, and it's controlled by the effective pair interaction. And so this average is calculated like that. So if we want to solve the Bogoliubov-Duhem equations via multiple scattering theory, again, it's trivial, but we just go by the ordinary way how we go by solving any multiple scattering theories. Just we have to remind us that this is now an enhanced complication of electrons and holes. So the basis functions we take have an electron and the hole basis function, and the Bessel function has a different argument in them, where the energy is replaced by these plus or minus quantities. This basis is of course orthonormal, and it's complete, and the free space Green's function, or the structure constants, what did I write there, can be calculated from the spectral representation or any other ways you wish, but there's no complication in that. You just have to notice that they are now matrices in A and B, which is just a notation for electron and hole. So each index can take an electron or hole. So it's a 2x2 matrix in this space. But you also notice that it's diagonal in this electron hole index, and yeah. So we can then define some scattering solutions, and these scattering solutions, of course, satisfy the same Lippmann-Schwinger equations, and if an incoming quasi-particle is an electron-like, then the solution of the Lippmann-Schwinger equation outside the muffin tin has also have electron and hole-like component. And the same way, if you have an incoming quasi-particle which is hole-like, then the solution of the Lippmann-Schwinger equation become mixed again, in electron and hole-like. And within these confines, you can still do the matching condition to calculate the T matrix here. To calculate the T matrix, the matching condition has to be from the outside, between the outside solution and the inside solution. The inside solution is obtained by numerically solving the the radial Bogoliubov-Duhem equation, which I recast it here in a very special way because of this analogy I want to point out is instead of a second order differential equation of 2 for the electron and hole, I created 4 linear differential equations for electrons and holes. And what you notice here that the 2 equations, this one and this one, are only involves electrons and holes only. This one couples the electrons to the holes with the delta, and the holes to the electrons with the delta star. And if you remember Julie Staunton's talk, she showed how to solve the radial Dirac equation for the muffin tin sphere, and you immediately will recognize that this recast of the radial Schrödinger equation is pretty similar to what Julie did for the relativistic case. So if you happen to have a relativistic solver, it's only a matter of hours to it's really trivial to rewrite it in terms of the Bogoliubov-Duhem equations. Here, in the relativistic case, there's a coupling between the kappa equal L and the kappa equal minus L minus 1 states, and the operator there is the spin orbit coupling, and instead of that now we have the coupling of electrons and holes via the effective pair interaction. The relativistic generalization is so trivial that I won't even bother you with. So I just sketched the idea that to conserve the idea of pairing, we come back that it's really a time inverse pair, and we have to recast the order parameter in terms of the time reversal operator here. And then the whole argument which I told you about Bogoliubov-Duhem goes through, and you get to a relativistic Bogoliubov-Duhem equation with the normal state Hamiltonian casted right here. So then the question is how to calculate the Green's function, and again you can follow the footsteps of normal state multiple scattering theory, and the derivation is easy to come by. You can get the Oak Ridge convention written here for the Green's function with the regular and irregular solution, and now you just have to realize that these quantities here with Q and Q prime are now a composite index. It's in a more complicated way that Q is kappa mu, and the quantities also have an index in electrons and holes, and the scattering path operator is constructed the very same way as it's been discussed by Hubert in his talk. And once the scattering path operator is calculated, then we are again in business, because from the Green's function it's possible to obtain all physical quantities like the charge density, or in this case the order parameter, which we often refer to as an anomalous charge density. So once we have a Green's function, I think Hubert mentioned that the Bloch spectral function is a real powerful tool in multiple scattering theory, because the Bloch spectral function can be calculated from the Green's function, and it gives you a delta function whenever you hit a band with E and K. And if you just add a little imaginary part to the energy, you can basically make a contour plot of the Bloch spectral function, and you get this band structure. This is just like a little projection out here. So what happens if we solve the Bogoliubov-Duhem equations? As this is a little toy model. If you studied KKR, you're probably aware that there is a generalization to one-dimensional square well potential, chains of one-dimensional square well potential, and anybody coming out of the Bristol school is the first thing is going to learn is to solve the KKR for the one-dimensional chain. So this is what I did here. If it's a normal state solution, I will get a band from this solution of the KKR. And then if I solve the Bogoliubov-Duhem equation, now that for a moment, let's imagine that it's not superconducting, so I just zero out these effective pair interactions. Okay, so if there's no interaction between the Cooper pairs, then there is no point in writing anything in terms of two electrons because they don't interact. And that's, however, I'm still solving the Bogoliubov-Duhem equation, so it's just doing it twice, right? So by construction, the whole-like component of the Bogoliubov-Duhem equation is a mirrored image of the electron of the normal state solution. So in this case, this part would be 100% electron, and this case would be 100% hole. Now, if I switch on these off-diagonal potentials, the effective pair interactions, then what happens is a gap opens up between these two branches of the band structure. This gap is called the superconducting gap. It's the binding energy of the Cooper pairs. That's how you can think of it. And every point in this band structure now is a mixture of electron components and hole components. You cannot say anymore that the upper part is, say, electron or lower part is hole. So this electron-hole idea of an analogy with semiconductor physics comes from the fact that if I solve the Bogoliubov-Duhem equation with the delta equals 0, that is like a semiconductor analogy that I have a band which is occupied and another band which is not unoccupied. But you remember that the Bogoliubov-Duhem equation is a Bogoliubov-Volatin transform of the two electron Hamiltonian. So now the electron and hole carries the information about the Cooper pair. And that's why these states are, these Bogolon states are both electron and hole-like. So what happens if I do it for the real world? Easy first, just to do the niobium. Niobium is the superconductor with the largest available gap. And now we solve the Bogoliubov-Duhem equation again with the delta set to 0 here, and the density, and calculate the density of states. So you find that there is a electron density of states and the hole-like density of states. The electron-like density of states should be exactly what you would get in the normal state, and the hole-like density of states is the mirror of it on to the Fermi energy. Now if I switch on the effective pair interaction in the Bogoliubov-Duhem equation, I obtain a superconducting gap right here. And in principle, I shouldn't extend the energy range this much because the theory loses its value, but mathematically this can be done. You see that this symmetry of the electron hole appears again in the density of states as well, but there is a superconducting gap opened up, and this gap, the size of this gap is exactly the delta I gave it to. This is a source of great confusion, so bear with me in the future. So if you want to do the same thing within the screen KKR, which Laszlo was talking about, there's nothing to do, just do the screening transformation on the Bogoliubov-Dujan equation, and because the structure constant is diagonal, it is really trivial to do. So we can apply the machinery Laszlo was talking about to calculate inhomogeneous systems, which in this talk will be include some geometry, so overlayers of heterostructures of superconductors and overlayers and impurity systems and other nanostructures. Okay, so what happens? There's one nice experiment of Yamazaki and Nick Shannon, who measured the critical temperature of gold and iron overlayer put on niobium bulk. So forget for the moment, forget about this iron. That will come as second part of this bit of the talk. But right now, I will just look at assume that there's a gold layers on top of niobium bulk. And the question is, what do we expect if we solve the Bogoliubov-Dujan equation for this system? Now, first of all, you have to define what is superconductor and what not. And we know that niobium is a pretty good superconductor with a large gap, and the gold is not superconducting at all at any temperature. So it's quite logical to say that I'm going to put an effective pair interaction on the niobium atoms or niobium layers and a 0 where I see gold. And of course I put 0 on the vacuum. I haven't seen superconducting vacuum. No. So anyhow, what we know from physics is that at the boundary of a superconductor and a normal metal, there is a effect called Andreev scattering. Andreev scattering is the means by electrons and holes can move between one method to the other. So if a normal state, there is an electron, and it goes into the superconductor, it pairs with another electron, and the hole goes back into the normal metal. And this is right now not to mix with the Bogoliubov-Dujan electron and hole things. These are just real electrons. And so the beautiful thing is that because we do scattering theory, our scattering path operator includes these kind of processes naturally. And if I solve this system now with this kind of effective pair interaction, what do I expect? In the niobium, I expect to see a gap, but I don't know what to see in the gold, right? That's the question. So that's just some calculation details, that how many layers and whatnot we take. And so even the normal state is really funny for the system, because here is the band structure of niobium in a way you probably never seen before, is by integrating the niobium band structure in the 1-0 direction. So it's more like a mixture between a band structure and the density of states. So there are and I plot it again along a k value, which is diagonal in the 2-dimensional Brillouin zone. And here then you can see that there are regions where are lots of states in the niobium, and there are regions where are a lot less states. There are regions where are no states at all. So in these regions where are not many niobium states, quantum well states form. they feel locked in to the gold because they cannot penetrate into the niobium and it cannot penetrate into the vacuum as well. So, and then you get these quantized states with 2 pi over L, L being the box size as the frequency. And whenever they go into the region where there are a lot of niobium states, they smear out completely. So now what happens if I apply Bogoliubov-Duhem to this system? I expect this, you should know by now, is that here is this band, and I expect this to invert for the whole. And if I switch on the delta, I expect the delta, a gap to open here. And that's exactly what happens. However, you have to do it with every single branch of the quantum well states. Now, there's one thing you have to notice about this plot, that the energy range here is the energy range of the gap in the niobium. So if I would calculate the states in the niobium from Bogoliubov-Duhem, I would get an empty white square here because there's not a single state in the superconducting gap. So right here, nevertheless, I see quite a few states remain in this superconducting gap of the niobium, but there is also a gap within the niobium, which is now much smaller than it's been before. So this is what happened. We got the K-dependent gap. We got band sharpening. So those states which were here are now sharpened up because these could penetrate into the niobium, but they cannot penetrate into the niobium in the superconducting state anymore.
This is for the gold interface layer. So
this is one layer out of 30 layers. I don't know what the calculation was, but you can think about it as in the middle. I'll come that into in a minute. So Hubert's question is very good. So let's look at the what happens if I can operate this. What happens if I step from the niobium all the way over the layers and I calculate the Bloch spectral function along 1K, and I'm going to plot that for every layer. Unfortunately, I can't stop it, so here is where I am, the layer. So there was an interface state here which slowly disappears if I step to the gold. And there's a state formed. I think I put the wrong figure on this slide because this is the normal state. But nevertheless, the point is that these quantum well states were pretty regular in the calculation. And if I calculate now with the Bogoliubov-Duhem, and I don't want to go through this video again, I'm going to integrate the video into one single picture. And see, there's two scenarios. I don't know how gold grows on niobium, so can be BCC niobium and BCC gold, or there can be BCC niobium and FCC gold. And what is obvious from these figures, that there are these quantum well states which open up a gap every time. But what's really striking is that there is no dispersion here. So the answer to Hubert's question, it doesn't matter which layer I'm looking at because all of them are the same, except these are from some interface states in the BCC structure, which is not present in the FCC structure. These actually locate to the first couple of layers, and they disappear later on, as you could see on that video. So the striking thing is that the gap is the same in each layer, what is being induced in the gold. So this is the first real test we did. This is the Yamazaki experiment I was talking about, where they put niobium 400 angstrom and put some thickness of gold on it, and they forget the iron at the moment. They measure the critical temperature of this heterostructure, and what they see is up here on this figure that it decays as the thickness of the gold changes. And this is the figure what we made. The red dots are exactly the experimental points digitized and put some error bars on it. And the blue curve is not a fit, but the calculation from the Bogolyubov-de Gennes. And this was the very first time we started to be confident that this method is actually working. Okay, so then we went gaga and put all sorts of materials on top of niobium, not only gold, but silver, aluminum, molybdenum, iridium. And out of this, in my lab, people tried to do silver and molybdenum. And although not such a good agreement as with the gold, but pretty good, was observed for silver and molybdenum at the moment. Aluminum is a complete mess because that doesn't grow on niobium and forms islands, and the whole theory breaks down. So, if you studied superconductivity, you know that something has to decay from niobium, and for me it was quite a shock that it wasn't the gap. But it turns out what is decaying is the superconducting order parameter. The superconducting order parameter, which is obtained from the electron hole of diagonal Green's function, the same way as you obtain it as you obtain the charge density from the electron or the whole hole part of the Green's function. That's why we call it as the anomalous charge density. And the anomalous charge density can be integrated for the Wigner-Z sphere, and you get an anomalous charge the same way as you get a charge per layer for a calculation like this. And you can plot it layer by layer, and you see that this is the one which is really decaying, and even the tail matches this 1 over x function, which has been predicted by Falk. So now, I hope you followed this, and now we have this thing that I told you that the order parameter and the gap are two different quantities. In bulk, it isn't. It's the same thing. That's why this is often called this delta effective, the effective pair interaction. They often call it as the gap function. It's the gap function in bulk. But in a heterostructure, that's not true, because we set delta to be 0 in the gold, but nevertheless we found the gap in the spectrum. So the two quantities now became distinctly different. And a little picture emerges from this, how proximity in superconducting state actually works. The Andreev reflection between the superconducting state and the normal state fills the normal state with Cooper pairs, and the Cooper pairs then lose some of their binding energy crossing over to the normal state, so the gap decreases. But what you find is the order parameter, which is basically the probability to find the Cooper pair, decreases as you go away from the superconductor. So this is how what this picture suggests, and there is a way to check it. So that's what we are going to do, and the check is to look at the surface state. The gold has a wonderful surface state, and the surface state is localized to this top layer or around that. So if I would calculate the surface state spectra, question is whether I get a gap in the surface states or not. If I don't get a gap in the surface state, that means it doesn't participate in the Andreev scattering process and never forms a Cooper pair. And so I calculated the surface state immediately with Bogoliubov-de Gennes with delta equals 0. And I find this nice surface state here, just crosses. And there's all sorts of other states out there. And if I switch on the effective pair interaction, indeed what I find that all other states open up a gap, they sharpen up, and they do what they're supposed to do in this situation, except the surface state, which doesn't care about. So my prediction in this case has been approved by this computer experiment. Okay. The surface state story becomes more interesting if I apply it to a topological insulator. So there's a palladium telluride and bismuth selenide, where palladium telluride is a superconductor and bismuth selenide is a topological insulator. So we put a couple of layers, quite a couple of layers of bismuth selenide on top of palladium telluride, and we see what happens. If you just look at semi-infinite bismuth selenide, you find this famous Dirac cone in the spectrum. And now, if I put the bismuth selenide over the palladium telluride, it comes by these quintuple layers, units of periodicity, and you put 1, 2, 3, 4, 5 quintuple layers, you see these states form here. At the end, there's actually the Dirac cone, but there's something else here. And if this is an integrated picture, so if I look the topmost layer, then there is the clean Dirac cone here, and on the bottommost layer, just closest to the palladium telluride, there is another interface state happening here. This is wonderful to test out my theory. I say the bottom band will pick up a gap and the top gap is not going to pick up anything. That's the prediction. This is just a little description of that again. Oh, sorry, I forgot to mention that these other states, these are just ordinary quantum well state. Right now, they are not too much to be concerned about. Okay. So do the calculation, put the delta on the palladium telluride and the 0 on the bismuth selenide. It's not superconducting at all. I really get to the point where I plot the spectral function at k equals 0 here for the Dirac surface state and for the bottommost interface layer. And you see that the Bogoliubov-de Gennes solution is split into two, while the surface state there is no split at all. You get the same delta function over there. And these quantum well state, they do split as well according to the solutions. So this is something of interesting because there was a little quarrel between two experimentalists, one saying that the surface state has the same gap as these quantum well state have, and Xu had a experiment where they said it's very different from the quantum well states, and from our calculation, we can say that we support the results of Xu at this level. So what happens if I put a magnet on the superconductor? Magnetism and superconductivity usually doesn't mix because the magnetic field is coupling to the up and down Cooper pairs, and they try to align them so it breaks the Cooper pairs. The Bogoliubov-de Gennes equation gives you exactly this. It's like some layers, 12 layers of iron put on niobium. You see that the niobium density of states really shows this superconducting gap, but the density of states of the iron is not at all 0 in between the gap region. So this is now towards the experiments of Yamazaki, where you put some gold and some iron layers on top of each other. And if you remember, I'll show it in a minute, what the experiment was saying, it starts to oscillate. The TC starts to oscillate. It's quite a puzzle. So what happens is, this is just a normal state calculation here, that what you see is just the density of states in this top niobium layer, in the gold layer, and the first iron layer. And what you immediately notice that the spin-up electrons, they are confined to this gold, so the quantum well states are sort of sparse, and the spin-down electrons can freely move from the gold over to the iron. And so they are locked in a much bigger box. So 2 pi over L is the frequency, so they got more frequent, and so this is more dense. So now if you would pick a Cooper pair out of this, that's a problem, because I said the Cooper pair is a pair with a k and a minus k, but it's impossible to pick anything with a k and a minus k when the possible states are actually quantized. So the only way you can form a Cooper pair that it will have a moment, a net moment. And actually it's been worked out by Fulda, Ferrell, Larkin, and Ovchinnikov, that in this case it's still possible to form a superconducting state, but the order parameter is going to oscillate as this difference in the momentum dictates it. So we calculated the anomalous density for this system, and indeed we find the decay I described before, but on top of this decay there is an oscillation with a very nice and definite frequency. And so we now argue that this oscillatory behavior of the TC of this iron gold niobium system is due to the oscillatory behavior of the order parameter. Well, if you really carefully look at, there's a problem though, because this thing doesn't really want to decay at all, and for that I don't have an answer. So we still need some further studies for that. There's another interesting phenomenon called inverse proximity effect, where you put very thin layers of niobium and very thin layers of gold and very thin layers of niobium again. And what happens if the gold layer is really, really thin, then the TC actually goes up. This is also a measurement from Yamazaki. The same thing was measured in lead and silver. When the lead is really thin and the silver is also very thin, there is an increase in TC, and then there is a decrease. If the lead is too thick, this is all gone away. Now this time I can do density functional full time. So I'm going to use this functional which I mentioned here. I'm going to calculate the electron phonon interaction. I can calculate the order parameter, the chi, the anomalous charge density, multiply them together to get a delta star, and I'm going to close the self-consistency loop with this really approximate functional. Don't be fooled that this is the same capital lambda. This time I just noticed it's small lambda because it's layer dependent. Every layer is going to be. The way to calculate it is been defined by Macmillan. It's very easy. You just calculate the density of states at the Fermi energy, the mass, which should also have an I index in here, the average phonon frequency on that layer, and this mysterious parameter called the Macmillan-Hopfield parameter. And the Macmillan-Hopfield parameter can be calculated by the Gaspari-Jurphy formula, which is again fairly easy because it includes quantities like density of states. This delta is the phase shift on that layer, and the free density of states. So it's really suited for KKR because we calculate phase shifts during the calculation naturally. So it's rather easy to extract that information. And the only difficulty here is this average phonon frequency. This is the calculation was done by Stefan Schönecker with VASP as an extension, which allows this to calculate it. I'm just saying it very, very, very. So it's right. So this is the main reason this calculation can be done only for really thin layers or bulk. For thick layers, it's very complicated, and we couldn't do it. Not enough computer power. So in bulk, it's even customary to replace this with the Debye frequency. So we calculate the phonon dose for bulk is a quick test here. This is the experimental value. This is our work here. It's not too bad, but it overestimates it a bit. This gross column is the same as I always mention that Lüders and Lynching can do better than I can. So that's their result. Macmillan with the mu star is the Eliashberg equation, and the BCS is completely off the scale. So I would say that's not too bad. I just show you that you get the sense how well this really, really simple function out by just using one number works. So this is the calculation, and if you calculate the superconducting transition temperature, we are happy to notice that it's actually going up if we add one gold layer onto a slab of 3 niobium. That was the biggest calculation we could do for the phonons. The reason why this is going up can be understood from the phonon spectrum, that if I just add one layer of gold, there is a strong enhancement of the phonon contribution on the lower frequencies. It's called softening, and this phonon softening is not so pronounced if I put one more layer of gold on top of this. So this phonon softening on the surface is giving this, and this is why we are happy to say that we can somehow interpret these experimental results. How much time do I have, Didier?
25 minutes.
Okay. This is now we are getting deeper and deeper into explaining superconductivity with KKR. There's, as I mentioned, superconductivity and magnetism don't mix, except if you are lanthanum nickel carbon or lanthanum nickel gallium, or if you are rhenium. Because in these materials, they have this measurement that when they cool it down and superconductivity appears, they actually start to have a magnetic moment. These are normally non-magnetic systems, and in the superconducting state, there is a magnetization. Not a big one, though, because they can't even measure it. You need a very special technique called muon spin resonance to measure these extremely small magnetic moments. Now, this needs a little finessing, because normal superconducting is not going to describe this, because in normal superconducting theory on Bogoliubov-Dujan, such a state will not give you an energy minimum by construction. So here you need to introduce a concept of so-called triplet pairing, when pairing between, so far we always dealt with a singlet pairing where we had a delta in spin space which was spin up, spin down, spin up, spin down. So there's a Cooper pair was a spin up and the spin down electron. But now we have to do a thing that two electrons with the same spin can still pair. This is in principle impossible in a simple model with just one band, because the anti-commutator relations for the field operators, if that's translated into the order parameter, that's chi is a function of r and r prime and sigma prime. It has to be change sign if I change all the parameters like sigma prime and r prime. But with the if I have a spin in the same direction, it's impossible to have a local delta. Because if I have sigma prime different, then I can say, okay, I don't care about r and r prime, so the chi can be a local quantity, which means that delta is a local potential, just function of r. This one cannot be done for triplet pairing. So triplet pairing can be this approximation can be done only if there is more than one orbital, because then I can leave the r and r prime alone and exchange the orbital indices and still get the odd pairing. So here we are not only need to get some idea about the delta, but we also have to get some idea about the triplet pairing and the possible and the pairing between the various orbitals. And because of symmetry considerations, we only need to care about the nickel d orbitals. So there's the agenda now. Oops. Okay, so we will need to find some kind of a pairing scenarios, and these are all the pairing scenarios which you can put in. You can have a pairing like zx to the zy, xy to the zx, and all these, and you calculate the density of states. This is just density of states, and sometimes you don't get a gap. This is called a nodal gap. It's still a superconducting state, but it has a nodal gap. But there are some where you get a full gap. That's called the fully gapped state. So experiment says that both lanthanum nickel carbon and lanthanum nickel gallium is fully gapped. So these are actually off the chart, but I'm still going to include one just for fun, one nodal gap state in my further investigations. In the lanthanum nickel gallium 2, it's easy because there is only one fully gapped state, so that's what we are going to use. So we fit this phenomenological interaction strength to get the experimental value of Tc in both materials, and then we calculate with various pairing models the specific heat and fit it to the measurements in order to fix the triplet pairing interaction. And then we see whether with these conditions we can get a magnetic state. So this is what I told you. I assume the pairing with z squared to and xy, and z squared to xy minus y squared, and also zx minus zy. This one was giving me a nodal gap. So this is here just for fun, and you can see that it's not giving you a very good fit to the heat capacity. The two fully gapped combinations, they actually gives you rather nice match to the experimental observations, and out of which this one gives a slightly better one. So we put our vote on this this pairing with pairing interaction strength. For the lanthanum, nickel, gallium 2, there is only just one state to consider, so that gives a fairly good fit, so I'm happy with that. And then we do the Bogolyubov-Dujan calculation self-consistently, and what we see is that once we get the to TC, magnetic moment starts to appear in both cases. They're rather small. If somebody comes up to me with this kind of moment size, I tell him the Brillouin zone integration is not right. But we couldn't make these numbers go away, so I think these are real. And the reason for this to appear is that spin-orbit coupling is mixing up the spin-up and spin-down components and causing them an imbalance, like the same way as magnetism is being caused. And this imbalance in the spin-up and spin-down density of states is giving you a small magnetic moment. Even the ballpark figures are actually, the size of the moments are not too bad compared to experiment, although I'm not too keen on comparing them. And the last bit, which sits on top of all the KKR calculations we can do now, is the Yoshiba-Rosinov states. If you want to understand Majorana fermions, the first thing to do is understand the single impurity on the surface of a superconductor, and this single impurity being magnetic. Why I say that sits on top of all calculations, because we have Kohn, Sham, Dirac, Bogolyubov, Dujan so far, and then screened KKR, and now embedding. So the physics here is that the magnetic moment of the impurity interacts with this with the Cooper pairs in the superconducting in some vicinity of this impurity. We are going to consider niobium 110 surface. And what happens is that they kind of try to align the spin, so it tries to break the Cooper pair. So it's, by other words, it weakens the Cooper pair bonding, and you will find some states within the gap. And Yoshiba, Rusinov even gives a formula how to do this. So this is the superconducting gap of niobium, and you get two states, and a pair of these states are called a Yoshiba state. So this is now Green's function embedding, the same way as Hubert described it 2 days ago, because the embedding formula is formulated on the level of the T matrices. There is really not to add to it about if you do Bogolyubov-Dujan. The only notice is that every matrix you see here is twice as big. And of course, you don't embed just one atom, you embed a whole cluster of atoms. And before you do the Bogolyubov-Dujan calculation, you do a normal state calculation to obtain the potentials, and then the Bogolyubov-Dujan calculation is then just a one-shot embedding calculation in this case. So this is just describe what this extended impurity is. I don't think I have to do this after Hubert's talk. Everybody should get. Tau matrix of the host is calculated. We have the T matrix of the host and the cluster, and we just express the cluster tau matrix in terms of the host and the perturbation, and then just use the Green's function formula to calculate the density of states. Here's nothing to be done. It's all real space, so our only thing to look at is the density of states. So this is just how we did it, just 1 or 2 impurity on niobium. This is for 2, just showing it from various directions, how we put it on the 110 surface. Actually, there were measurements on this system. That's why we chose it, when they put manganese on niobium, and experiments by the group in Hamburg. What you really see here, let's call your attention to this figure here. In the middle there is this gap. So how to interpret this is they have a superconducting tip and the superconducting host. And because of the superconducting tip, there is this empty region in between, which corresponds to the superconducting gap of the tip. And basically, what you want to compare to a calculation is when this middle is taken out. So to improve your imagination, they just made this compressed figure here. With this tip gap taken out, and what you see is there's a bunch of states here. In fact, there are 4 of them. And I said just 1 is expected because just Cooper pairs interact with the manganese moment. That's entirely becomes more complicated when the state starts to hybridize, and the crystal field effect can be studied here. Before I go on to the calculation, I just want to remind you that we are on a 110 surface of niobium, which has a C2V symmetry, and there are 4 irreducible representations, and these are the d orbital basis functions. Of course, it's all in a non-relativistic description. And the problem here, the fact here is that the s and p orbitals don't give any contribution to the density of states in this region. So we are free to use just d orbitals, and these and the label, instead of labeling our states with the irreducible representations, we can just label them with the d orbitals here. And this is what we get from the calculation with spin orbit coupling used. What you see there's plenty of, we also get plenty of states in this energy region, where we can study the role of spin orbit coupling, which is quite marginal in this case. The brown is a total, so you get, but you are happy to count them and find there's 4 of them. And you can calculate the spatial extension of these states, and because they come from this decomposition, we can even label them which is xy or yz. And then this can be compared to the experiment. And I think the comparison is quite fair. The major discrepancy here is that this top peak, which we have here, is further from the Fermi energy than it is for the experiment. The other peaks are, I would say, agree rather nicely, and even the symmetry of these peaks can be identified favorably with the experiment or a tight binding model, which the experimental paper also contained. So why 4? There were 5 D states. What happened with the 5th one? It turns out it's the xy minus y squared state, which is missing. And for this community, I can tell that I should have done a so-called fixed moment search for this calculation, but was too lazy, so we just scaled the exchange field. And by scaling the exchange field is not the same as doing a fixed moment search, but we could see that if I scale out the exchange field, the basically there is the U-Shiba states move out and the gap becomes free because the impurity is non-magnetic. If I scale it to too big, then the moment becomes so small, so big that it is destroying the Cooper pair. So the U-Shiba states exit the gap region on the other end. And in between, various states move differently, and we see that the x squared minus y squared already been destroyed by the time we get to 1 in the middle of this figure, which would correspond to the normal exchange field. We can look at two impurities now. I don't want to do the same comparison. We have the same problem with this state being too low and not that up, and various issues, but the comparison is still very good in the case of a ferromagnetic arrangement of the two impurities. But in this case, you can actually rotate the moment, and this is what we did. Rotated the moments, and we see that there's one U-Shiba state which is changing rapidly. All others do basically not too much, but this one really crosses over the Fermi energy and goes into the other. And because it's the electron and hole component should be symmetric to the Fermi energy, it means that this thing is going to have a cross over here, and that's called the zero bias peak. And the zero bias peak, if you search that in the literature, that is going to be a hit, because right now everybody is trying to find zero bias peak in various nanostructures, because that's a sign of a Majorana fermion. I don't want to say I got it as a Majorana fermion, just a zero bias peak. So it has a very peculiar property that it's at the same time electron and hole. So, come to the summary. I hope I convinced you that we could successfully generalize screened KKR method to solve the Kohn-Sham, Dirac, Bogolyubov-Duchenne equations, and it's trivial. Plenty of applications from overlayers to surface magnetic impurities. I was trying to pick some applications where it can be compared to the experiment. So these are the ones where we were successful. I didn't show the ones where we failed. And Ubinitio theory now brings material-specific understanding of many experimental phenomena, which also brings deeper understanding. Maybe not much, just a little, but that will come. KKR brings unique advantages to this method. If you think about this impurity problem, in superconductivity, there's a fundamental distance. It's the coherence length of the Cooper pairs, the extent of the Cooper pairs. So if you would want to describe an impurity system in a supercell, as you normally do, that would be questionable, because the coherence length is going to couple them, so you cannot decouple two impurities in a Cooper pair, as far as I understand at the moment. So the coherence length is a major obstacle for other kind of calculations. We never used supercell throughout this calculation. Everything was semi-infinite, impurity embedding, and all that. And also I like to point out that multi-orbital theory, in the case of the lanthanum nickel carbon and lanthanum nickel gallium, gives new ways to think about these materials as exotic pairing. So yeah, thank you very much. What?
Strength.
Strength. Strength of what?
In different layers, you have different mismatch between lattices.
Um,
Strength.
strength of the effective pair interaction.
No. I mean, you're making launch layers, right?
Relaxation.
Oh, relaxation is a little problematic in this thing. One, we cannot do relaxations in the plane. In-plane relaxations out of question, because that would change the lattice constant from layer to layer. So Fourier transforming the layers so we can't do that. Perpendicular relaxation can be done, no problem. However, there will be some limits to that because of the sphere sizes being too much overlapping or not covering the space, or that kind of problems will enter. So a little relaxation. Sorry?
In ASA.
In ASA, yes, in ASA. Yeah. But muffin tin is not possible for layers, because the muffin tin 0 would change from layer to layer. So you have to have ASA in this layered calculation. And yeah, some relaxation is possible, and we do it, but much relaxation is problematic.
Thanks for the lecture. I have a question about the triplet pairing. So, is it possible to interpret such pairing through a strong Fock exchange mechanism, or it's completely different?
Oh, I think that's very different.
In what sense?
I'm not really familiar with that, but I would think it's because of the how you satisfy the anti-commutator relationships for the Cooper pairs.
John?
Yes, John?
So I'm wondering, you had a parameter which was close to phonon, electron-phonon interaction. Is there anything analogous? Can you see an analogy, say, with Eli-Ashberg theory, how they determined that it's a completely different.
You are asking too much from me, John, because I'm basically a KKR person, and I just jumped into this superconductivity from the direction of KKR and not from the direction of superconductivity. And I have to admit that I still see it as a big pile of papers I have to read.
Other questions?
No.
Yes.
Question is because there is a formal connection between what he's doing and what you're doing.
That's what I was asking.
Yeah.
I,
That's something different.
yeah, I would think it's a different route, because we go for DFT and Eli-Ashberg goes by the mu star. And
But there's a direct connection to the electron-phonon interaction. I didn't quite see it in your formula.
well, but I didn't really include electron-phonon interactions in a dynamic way. I just
It should be in the theory. Anyway,
no, it's an auxiliary input to the theory.
If I may, I'm still a bit uneasy with the fact that if you've got niobium and gold up on it, that you've got a non-zero gap, or let's say constant gap for all the gold states. So does it mean, if I understand correctly, you argue with this Andreev scattering? So that means, could I see it as kind of an artifact that you've got infinite conductivity, for example?
Yeah, I assume a totally perfect crystal. There's no kind of scattering. I don't know any. I didn't say anything about electron-phonon interaction in gold, which might, the thing is that once the Cooper pair Andreev scatters into the gold, then they don't. There's nothing to change their status.
But they could scatter let's say, from the
But
surface of gold, or not?
yeah, well, that's why their binding energy is smaller. So when they scattered over from the niobium to gold, they don't have the same gap. They have a smaller gap. So the binding energy is smaller, but they keep that binding energy in a perfect theoretical model ad infinitum. It's just there. The possibility to find the Cooper pair very far away from the superconductor is very low.
Ah. Oh, nice, that's not that. Okay.
Anybody else? No, so thank you again, Bálazs. You deserve your dinner.
Great.
And a beer.
Laurent, do you mind closing the door, please?